This thing has been behaving a little bit badly lately. Okay, so let's talk about what we've got going on this week. We'll have a quiz on Friday. And there'll be a homework due on Wednesday, not Friday, at 7 a.m. Okay, and then let's see, what else is going on? I've got help session. Actually, if you're looking for help, I'm going to be around this afternoon, so you could come by and ask for help. My biochem lab, once again, this week is kind of on their own. So I'm going to be kind of jumping around between upstairs and lab and my office. If you want to come, let me know after class. Also, maybe you could send me an email. But if I'm not in my office, try upstairs, one floor, right across, upstairs and across the hall is where the biochem lab is. Okay, probably one of those two places. Also, there's a help session on Google Meet on Thursday evening. And for help in these sorts of things, you should feel free to stop by. I'm happy to just work problems with you. Okay. I had another thought about that sort of stuff, but I've forgotten it, so maybe I'll come back to it. One other thing is I got a migraine starting last hour. It affects my vision, so you guys are going to need to be on top of me and catch my mistakes more than usual. Okay. Questions on what we're doing? Okay. All right, then what we're going to do is talk about pH today. But the first part of talking about pH is actually a good review for stuff that we talked about last lecture. So if I have water, like you had the problem with ammonia, right? Where ammonia could act as an acid and a base, and you had to draw the conjugate acid and conjugate base for ammonia. So water also can act as an acid and a base. All right, and once again, I'm gonna use these arrows from organic chemistry that I'm not making you responsible for, but they might actually be helpful in terms of when you think about drawing acids and conjugate bases. One thing to remember, so an acid, well, let's go and do this. Let's call this an acid, and let's call this the base. All right, an acid does what in water? So an acid, well, let's talk about that, and then we're going to use both our definitions here. What is an acid? What's the definition of an acid? All right, I'm here for proton donor. We'll go with the proton donor. That's the one I want, all right, for this. Because even though we're in water, we're not going to make an H plus here. Right, an acid, we'll dissociate to make H plus in water, but we're not going to make that right here. So an acid is going to donate a proton, which means that this water here, if we're calling that one the acid, it's got to give up a proton. If this one's a base, what's the definition of a base? It's a proton acceptor, so it has to accept one. And so this is where those arrows help out. If something's a base, it's going to accept a proton. It's going to accept them on one of these lone pairs of electrons. The lone pair of electrons is going to go grab a hydrogen, essentially. So what we would do here is, if I'm drawing the arrows, this pair of electrons is going to go grab that hydrogen. It's going to make, when it grabs it, it's a pair of electrons. Two electrons make a bond. It's going to make a bond with that H. And so if I write the products here, I'm going to have a hydroxide, right? And then I'm also going to have, so it's going to lose, actually, let me draw one more set of arrows. Those electrons that were in that bond are going to go onto the oxygen. And then the other one is going to gain a hydrogen. We had that top pair of electrons go and attack the hydrogen. And so we end up with that. Okay? And I'm drawing charges here. So you have an equation for figuring out formal charges that you used last semester. I'm going to unless I remember in a minute or two, I'm going to let you look that one up just from earlier, right? So formal charge in the back of your book, or formal charge on the internet, really. How do I calculate formal charge? But what I want to do is give you a set of simpler rules here that I've talked about before. So here I have how many bonds to oxygen? 1 bond to oxygen. That's going to equal -1, or 1 minus we're going to do because it's a charge, okay? Whenever oxygen has 1 bond, you put a minus charge on it. So I put a minus charge there, okay? Whenever, how many bonds to oxygen on this other one? 3 bonds to oxygen. And that's going to equal +1, okay? And so I put a plus charge here. All right, if you go back and look at your formal charge rules, here, I will write the equation right here. So formal charge is going to be equal to the number of valence electrons, okay, minus the number of bonds, okay, minus the number of unpaired or unshared electrons, I should say. Not unpaired, unshared electrons. Okay, and if you apply those rules, you'll get the same answers here. All right, but it's much easier if you just remember 1 bond to oxygen is a negative charge, and 3 bonds is a positive charge. Okay, and 2 bonds is neutral. Yes.
Is that the same thing as saying the normal amount of bonding areas for the neutral amount of bonding areas minus the number that it already has, or the number that it has?
So you're saying, is it the same as saying the neutral bonding minus the number that it has? Because it has, neutral would be 2, and I'd subtract 3, and I would get a -1. So you'd have to flip those.
Flip it around.
You'd have to flip those, and you probably get the same. That probably works.
Okay.
I haven't done that.
That's how I think of oxygen. I'm like, oh, it has 2. If it
Right.
has an additional one, that's +1.
When you guys do Lewis dot structure rules, there's some things you can do to help here, but you should follow Lewis dot structure rules that you were taught. Okay, there's a way to do it. There are multiple ways to do it, but you were taught some sort of method. You should follow that method. But in terms of things being neutral, a carbon with 4 bonds is neutral. Okay, anything in this column with 4 bonds is neutral. Anything in this column with 3 bonds is neutral. Anything in this column with 2 bonds is neutral. Anything in this column with 1 bond is neutral. Okay, so for neutral, 4, 3, 2, 1.
Phosphorus do 5. Isn't there one that has an exception that does?
We can do more bonds because some atoms. The question is, can phosphorus do 5? Phosphorus can have 5 bonds because it can expand its octet. Okay. But let's do the simple case here. And we did talk about expanded octets last time. So let's go ahead and, or we did talk, last time was last semester. Okay. I've got an acid here, right? This first water is our acid, and it becomes this. So what is that? What do we call that? The conjugate base. And this was a base, and it became this. What is that? Conjugate acid. Questions? Okay, great. All right, so what this is an example of up above is that is the example of the, or I'm going to say it is the example, not really an example. The equation up above is the autoionization of water. And I'm going to say the chemical equation. All right, so in other words, water can act as an acid and a base. And because it can, water can actually auto-ionize itself, right? So we've got water, both those waters on the left are neutral, and then we have charged things on the right. A charged hydroxide ion and a charged hydronium ion. So we can write a equilibrium expression for that. All right, let me put the phases in, and then you do that. So it's water's a liquid, and this water's also a liquid. And then a hydroxide would be aqueous, and so would hydronium ion. Write a K equals, right? K equals products over reactants sort of thing for that equation, applying the rules we know. Okay, so I'm going to do it right here at the bottom. I'm going to do, so we would do Ka, right? We're talking about an acid reaction. We normally do Ka, water special. I'm going to call it a Kw. It's a specific constant, okay? But you don't need to worry about that outside of that. It might be given on that equation sheet, right? There is no other Kw. Kw is going to be equal to, I'm going to go ahead, the hydroxide concentration times products, right? Times the hydronium ion concentration. And then what do I do on the bottom? Nothing, because water's a liquid, right? Okay, I wrote that to trick you. Actually, I was going to just pull it down, but I'm going to have to rewrite it, looks like. So, so there is nothing on the bottom. We don't worry about the reactants here because they're a liquid. If they were a solid, we also wouldn't worry about the reactants. Okay? And that's equal to a special constant, which is 1.0 times 10 to the negative 14th. That's what the equilibrium constant is for water's auto-ionization. All right, and this is really important, and it's going to lead into we're going to talk about a discussion of pH here. Questions? Okay, so before we move on to pH, because that's what we're after today, let's just use this equation we just came up with. So what this tells us is that the concentration of OH minus in water and H3O plus in water are related. Okay? Which actually makes sense. Do you remember Le Chatelier's principle? You may not, because it's been a break and you took the test and it was traumatic and all sorts of things like that. But super useful. Okay, super non-math useful. So Le Chatelier's principle says if I have something at equilibrium and I add something to one side or take something away from each side, it's going to shift to compensate for that. All right? And so if I add more H plus to solution, this is going to shift this way, and it's going to get rid of some of my OH minus, right? Okay, same sort of thing. If I add, as OH minus goes up, H plus has to go down. Does that make sense? Okay, Le Chatelier's principle tells us that. Super easy way to do it without using math. The equation also tells us that, right? Has to be equal to this constant, so if I make more of this, I have to take away that. That make sense? Okay, go ahead and do A. I'm not even going to work an example. All right, this is just equilibrium constant stuff. Go ahead and solve for the OH concentration in a superacidic solution. Sort of acidic. Pretty acidic. That's like in the range of what the acid in your stomach is. And if you're not sure what to do, please call me over. Happy to answer, help you out, get you started. Yes. So let me emphasize something I talked about. We talked about this last time, but remember that H plus is equal to H3O plus. Now the same thing, right, is equal to protons. All those terms get used, okay? So we say H plus, but it doesn't really exist like H plus, so people like to use H3O plus, and it's certainly much, if we're explaining what's going on with autoionization, we want to use H3O plus, but often we'll abbreviate it just back to H plus because chemists are lazy, okay? So let me go ahead and work this one, but if you were stuck there, I apologize. I should have reminded you of that. So we've got 1 times, or 1.0 times 10 to the negative 14th is equal to our concentration of OH minus, which is what we're solving for. I'm just pulling the equation down from up above, times our concentration of H3O plus, which is 1.0 times 10 to the negative second molar. Okay. Remember, these brackets mean molar. Okay. So now I just need to divide both sides by 1.0 times 10 to the negative 2 molar. 1.0 times 10 to the negative 2 molar. That goes away. All right. And so my answer here, I'm carrying my units, but when we use these equilibrium constants, they don't have units. So you just need to remember that we're dealing with molars. Molars are what our answer is going to come out with. Okay, so the answer here is not going to be 1 over molar. And so I could put that into my calculator, and what I would get is 1.0 times 10 to the negative 12th molar is equal to my hydroxide concentration. All right. And if you use the brackets and you just put the number, that would be okay because the brackets mean molar. You could also write molar to be safe, which is redundant, which I just did, and that's okay too. Okay. I'm comfortable being redundant with that sort of stuff. Questions on that? Okay, then let's go on. We're going to talk about pH. So pH is it's useful in various ways, but one of the things that's really useful is it shortens how many words you have to say. Okay, how many things you have to write. It's a quick how acidic is the solution, and you could just say, well, it's blah. Okay. So in terms of our solution up above, if I wanted to talk about how acidic something was, I'd use my, this is the concentration of H plus, right? Okay, but saying it's 1.0 times 10 to the negative 2 molar is the hydronium ion concentration is really kind of a lot of words, right? And so you don't want to write that, you don't want to say that, so you could just say it's pH 2. All right, that's how we shorten that down. And so what we have is this way of expressing how acidic something is. So pH is going to be equal to the negative log of H plus concentration, or hydronium concentration, or proton concentration, all the same thing. Okay, so that's an equation we're going to use to convert this to make this easier to talk about. We could also talk about POH is equal to the negative log of OH minus concentration. So we can talk about a POH. We're going to have this P something that we're going to use in chemistry a number of times. And what it means is negative log of whatever. All right. So let's go ahead and calculate the pH of a solution. Let's actually, but I will show you one more thing and then we'll calculate it. We'll double check it. So your book has this nice example where it talks about 0, I've got a concentration at 0.0214 molar H plus, right? Could also be a hydronium ion. That's the same as saying 2.14 times 10 to the negative third molar H plus, right? I just put that into scientific notation. No big deal. Another way I could say that, though, is I could say that's the same as 10 to the negative 2.67. All right, which means if I raise 10 to that power, I'm going to get that number. All right, so go put that in your calculator. Get your calculator out. We're going to practice using our log buttons. Practice, should also practice using, I had somebody else last hour who was having problems with their EE key still. So we want to practice using your EE keys as well. All right, and if you're having issues and not getting the same answers, come talk to me. We'll figure it out. Common mistake to not be using that EE key correctly. All right, so let's do this. 10, take 10 in your calculator, raise it to the 2.67 and see if you get pretty much that. It's going to be a little off by rounding error. All right, when I do that, that's what I get. So I'm going to go 2.67, make it negative, and then I'm going to take the log of it. Oh, it didn't like that. I must have done something wrong. Well, I don't want to take the log of it. Need to take the anti-log. 2.67 negative, and then anti-log. There we go. And so what I get out of it when I do that is I did indeed get 0.0021379, blah, blah, blah. Okay, which rounds to 214. Questions? So you see, if I was to take the pH here of this, it's negative log, right? So the pH of this is, take the negative off, 2.67. Questions? Okay. I am absolutely not going to enforce this here, but actually the significant figures aren't quite right there. When you do logs, these are significant and that's not. Okay, but I'm not gonna worry about it. For those of you who care, which probably is none of you mostly, that's how logs work for that. Okay, questions on that? All right, so we're going to work some problems with those, but I want to just show you a relationship first. This is a nice figure from your book where it shows that if we're looking, remember that our H plus concentration, our OH concentration are related and inversely correlated. When our H plus concentration is really high, our OH minus concentration is really low, and then our pH here is going to go like that. So if you look at this, our pH, if I have 1 times 10 to the negative 1, it's what this exponent is, right? It's 1. If I have 1 times 10 to the negative 3, it's 3. If it's 1 times 10 to the negative 7, it's 7. Okay? And then if this isn't a 1, then we have to correct for that. Okay? When we take the log, it's going to be a little more complicated. One other thing I want to point out is, so you guys probably have heard of pH before, and what's neutral? It's right up there, right? Neutral is pH 7. You may have heard that, right? And neutral is where you have the same concentration of H plus as OH minus. Okay, questions? All right, so let's go ahead and just work a quick problem. I've got a nice, this is the sort of problem I would love to ask you on a quiz or test, so I probably will. But we'll work it out in a second. But let's just say, I'm not sure about this, but the let's say the pH of orange juice. Well, let's the pH of your stomach is roughly. I mean, it's going to be different for everybody, and depending on what you've eaten, it's got a range. But let's say it's roughly 1.54. That's not actually really roughly, okay? What is the H plus concentration in your stomach? Okay, and I'm giving you a real number here about where that is. So what we have, if we were to work that, is I did this the hard way, right? We're going to have to do an anti-log. So pH, I'm going to remind you, is negative log of H plus concentration. If I go down here and I say 1.54, that's equal to the negative log of H plus concentration. And now I need to get rid of my log, all right? First thing I'm going to do is I'm going to take both sides times -1. So that's going to become a positive and that's going to become a negative. Are you guys okay with what I just did? Okay, so I'm going to do that, and then I'm going to take 10, because log is a log base 10. I'm going to take 10 both sides or raise 10 to both sides. Okay, so on the left there, here's practice of using that key. I'm going to go ahead and on my calculator, I put in 1.54. I make it negative. Some of your calculators you do negative first, and then I find my 10 to the x key. So on mine it says shift and then log. And what I get from that is that this goes away, and that gives me 0.0288. I'll correct it for sig figs in a second, is equal to my H plus concentration in my stomach. Okay? So that's molar because I've got brackets around it. Let's just make it molar like this. And then my original problem had 2 significant figures based on the log, but if you called it 3, it's fine. So I would actually take this down and go 0.029 molar. Okay? For you significant figure junkies. Remember, in terms of significant figures, if you're 1 off, it's okay. If you're 2 off, it's okay. If you're 3 off, I think it's okay. And then when you're 4 off, it's not. All right, so you need to be close. You need to be close, and you need to not give me 1 significant figure when it's not 1 significant figure, because that changes the answer a lot sometimes. Questions? All right.
What?
Yes.
Did you press, like, what button did you press on?
So your calculator, I think this is your calculator. So your calculator is going to be a little different than mine. So what on this one, I think I have to press the minus key first. So for the number, let's go back and put the number on there. All right, so 0.154. So I would put in negative. Oh no, actually I've got to press the log key first here too. And I'm sorry, I've got bad vision. And oh, there I found it. Okay, so under the second key on the left-hand side, there's the 10 to the x. So I would press second 10 to the x, and then it's giving me a little parentheses thing. Then I'd press negative 1.54, yeah, and then close parentheses, and then equals. Does that work for you?
Yeah, I got it.
Great. Thank you for asking about that. Other questions? Okay, so I want to give it, so we've got an equation here, right? We've got 2 equations. We've got this, we have 3 equations actually so far. So we've got pH is equal to negative log of H plus, right? And we also have POH is equal to negative log of OH minus, okay? And then we have that final the equation we actually started with, which was 1.0 times 10 to the negative 14th is equal to my concentration of H plus times the concentration of OH minus. And I can use these 3 equations. You can see if I know my H plus concentration, I can figure out my pH, right? And if I know my H plus concentration, I can figure out my OH, and then I can figure out my POH. All right? So essentially, if I know my pH, my POH, my H plus or my OH minus, any one of those, I can calculate all the other three. Okay, and that's this next problem we're going to practice, which is one, like I said, I like this problem. So, hint, hint. I want to give you one more equation, though, that will simplify this. And we're going to derive it from what we've got so far. So you can take like negative logs of all sorts of things in chemistry, and it's often helpful. All right. So we're gonna do that in other ways. But what I want to do is I want to take this equation here, and I'm going to take the negative log of both sides. Remember, I can do anything into an equation as long as I do it to both sides. So negative log of 1.0 times 10 to the negative 14th, right, on this side. And then I have negative log of H plus concentration times OH minus concentration, like that, okay? Now remember, if it's a log property, if it's a log of something times something, I can break those out and separate them. So I can rewrite this as negative log of 1.0 times 10 to the negative 14th is equal to negative log of H plus concentration plus minus negative log of OH minus concentration. Everybody okay with what I've done there in terms of algebra? Do you see that this is this and this is this? So I can sub those in, and the negative log of 10 to the minus 14th is going to be 14 if I put that in my calculator. Okay, so you'll have a chance to put stuff in your calculator more in our next problem, so I won't have you do that. But, so we have another equation that'll help us out, and that equation is, this is 14 after I run it through my calculator, is equal to the pH plus the POH. And the nice thing about this equation is if I know my pH or my POH, it's easier to get the other one quickly. Okay. All right, so then let's go ahead and look at one of these problems where you know the pH or the POH or one of those four things, and then you have to calculate the other three. I want you to go ahead and do C here. All right, so go ahead and do this one. And I will scoot up here and I will remind you of your equations on the bottom. pH is equal to negative log of H plus concentration. POH is equal to the negative log of OH minus concentration. 14 is equal to pH plus POH. And 1 times 10, let's say 1.0 times 10 to the negative 14th is equal to H plus OH minus. Yes?
For the getting 14, does the negative on the log cancel out the negative of the 14?
Does the negative here, you're saying, does the negative here cancel out when we have negative log in front?
Yeah.
Yeah, the log, it doesn't cancel, but the log of negative 14 is going to have a negative sign in front of it. That makes sense.
Oh, yeah.
Right. If I take the log is this exponent. So if I take the log of this, I get negative 14. And then I make it positive. And the reason why we make it's negative log is once again, remember we have this log system because we don't want to say a bunch of words, so we don't want to say negative, right? The pH is 14, not negative, not for that, but it's 14, not negative 14. It is possible to have negative pHs, and that just means that it's super acidic. Yes? Here?
No,
Here.
there's actually-
I'm sorry, that's 10 to the negative 10. Good question. Anybody else have a problem seeing anything? You could. I'm not going to work it for the answer. But I want to give people a little more time.
I'm just asking because if you would have to.
If you are waiting and you want an extra challenge, go from pH to H plus using the equation, right? So you have to do your antilogs there, or we'll do that one. I can do that one in my head, and you may be able to as well. Give you one more minute because people seem to still be looking. Actually, do as much of a table as you want. I can do all these in my head because they're simple numbers. Yeah, they're all 1 point whatever, so I don't have I can't do logs in my head unless they're simple. But all right, so let's go ahead and look at this. Let's look at C. All right, so I've got this equation right here. I'm going to do the easy one first. Well, actually, I'm not going to do the easy one first. Let's go. We need to figure out the pH, right? We got the pH, or I'm going to figure out the pH from the H plus concentration. All right, so once again, I'm going to say pH is equal to negative log of the H plus concentration, which in this case is 1.0 times 10 to the negative 10th. Okay. If I put that into my calculator, I'm going to get I'm going to get negative 10, right? I'm going to get negative times, if the log bit, times negative 10. And a negative times a negative is a positive. And so I'm going to get 10. Does that make sense? Okay. Then I'm going to do this equation because it's easy, right? If I put 10 in here, 14, what plus 10 equals 14? 4. You guys okay with that without me? Okay. So I've got a 10 there, and I've got a 4 there. Okay. And then I need to figure out my hydroxide concentration here. So this one's a little harder. So if I've got POH is equal to the negative log of hydroxide concentration. All right. And so what I would do here is I would put 4 here because that was my POH, right? Over here. And that's equal to negative log of hydroxide concentration. I would swap my signs there, multiply both sides by -1 to get that. I would take both sides, take 10 and raise it to both sides, and that would end up giving me a 1 hydroxide concentration. If I put that into my calculator, is going to be equal to 1.0 times 10 to the negative 4th molar. Okay? Questions on that? Yes?
Is there any reason why you use like POH is equal to negative log of the OH concentration versus like going with the KW?
Oh, why I would use one equation versus the other? No. So I used a certain set of equations there. You could have taken a different path and it's just fine. Okay? As long as you get the right answers. And so if you've done any of the rest of these, so these pH things are pretty easy to fill in, right? Because it just has to add up to 14. So that's going to be 8, that's going to be 3, that's going to be 6, okay? And then because all these things for this problem were the 1 times, right? And so it's not a complicated log in between, it's pretty easy to do those as well. This is going to be 1 times 10 to the negative 6th, okay? This one's going to be 1 times 10 to the negative 11, okay? This is going to be 1.0 times 10 to the negative 8. So I'm just looking over at this 8 here, making it a negative. And this is going to be 1.0 times 10 to the negative 6. Okay. Questions? Okay, and the thing with the pH scale is it's a log scale. So if we look up here in this table, note that for every step of pH, for every time pH gets lower, lower is more acidic, for every step in pH I go down, if I go down to 6, I go down to, there's one step, right? It becomes 10 times more concentrated. It's shuffled by 2 steps. So the amount of acid, the amount of H plus, which is what can do things in here, in a neutral solution compared to a 0.5, 1 times 10 to the negative 5th concentration of H plus, that's 100 times is a step of 2. Okay, you want to keep that in mind. It's a big deal when the pH changes by a unit. It's 10 times as much acid or 10 times less acid. Questions? Okay. So like last class, I made it farther than I had planned today. So I'm going to, didn't let them out early. I know your hopes, we're getting hopeful there. But let me get back up here. So we're going to actually move on to the next part of the chapter, which is going to be, we're going to talk about how you calculate equilibrium concentrations of acid and base. And we're going to bring our ice tables back for that. But what we did is we worked a pretty complicated problem to do it. We worked a complicated problem that used a lot of the skills we know from class, or a lot of the skills we learned previously. So vinegar is 5% acetic acid. And we're going to, well, let's go 5% weight to volume. Okay, so if 5% acetic acid is added to water, this would be like the white vinegar you buy in the store. What is the resulting pH? All right, and I need to give you one more piece of information. I'm going to tell you that the Ka for vinegar is going to equal 1.8 times 10 to the negative 5th. All right, so this is going to be, we're going to do an ice table here, but we need to figure out some other things first. I'm going to write out the reaction here for you. This is acetic acid. It'll be aqueous, and it can dissociate in water to make an acetate ion, which is the conjugate base, plus H plus. All right. So I'm going to add, if I'm going to do an ice table for this, so initial change and equilibrium, what do I need to know? I'm going to start with a concentration here, but what do those units have to be for the concentration if I'm using an equilibrium constant? They have to be in molar, right? But now they're currently in weight volume. So we have to convert from weight to volume to molar. All right. So one thing we have to do here, so we've got 5%, right, weight to volume. I didn't tell you the volume. Is that a problem? You could just pick a volume. Okay, and that's what you do here. You pick a volume and you calculate how much weight you have then, right, if it's 5%. So we're going to molar, right? What's a great volume if we're going to molar? Liter, 1 liter, okay? or 1,000 milliliters. So what's the weight at 5%, right? We're saying I've got 5% then of 1,000. We'll solve for that. It's a percent, so I'm going to put the 100 in there. What's 5% of 1,000? If I put through this algebra, put it in my calculator, I'm going to get equals 50 grams. Okay, you guys with me for that? Were you with me for the setup? Okay, yes.
Where did you get the 1,000? Why would you just?
I made it up. So weight to volume is, where did I get the 1,000, right? So remember, weight to volume is grams per milliliter?
Oh,
Okay,
okay.
good question. Does that make sense? So weight to volume is grams per milliliter. We used a liter because it's moles per liter, right? So then it's going to be less math. There's going to be a 1. You could use 100. We could use 66. Okay? Okay. Questions? All right, I'm going to take this point out because actually we have one significant figure with my 5%, which is bad problem making on my part, but we'll keep going with it. All right, so that's how many grams, but I need molar, right? So I need what? Molarity is moles per liter. I now know how many grams per liter I have. I need to go into moles, right? And if I'm going to calculate grams to moles, what do I need? Molar mass. So the molar mass of acetic acid is going to be, if I look at, remember our acetic acid looks like this, right? I have 2 carbons in it, so 2 times 12.01 plus I have 2 oxygens in it, 2 times 16.00, right? And then I have 4 hydrogens in it, 4 times 1.01. All right, if I put that in my calculator and add that all up, I'm going to get 60.06 grams per mole. Is that what you guys got? Okay, is there a question on calculating molar mass? Okay, so molar mass, this is from last semester, I have 2 carbons, right? Okay, good. And I looked up on the periodic table. I didn't, because I haven't memorized, because I've done this for so long that I have some of these memorized. So I looked up on the periodic table, under carbon, I've got 12.01, and I did it for the rest of it. Other questions? Because I did that pretty quickly, because I want to get through all this, but I'm doing things fast, and like I said, some of them I memorized, yes.
How many decimal points do you want us to use? Because for hydrogen, I use 1.008.
It's fine.
Okay.
I want you to use at least 2 figures past the decimal point off the periodic table. Okay. In the end, there's going to be one significant figure, so it doesn't even matter that much. But I would carry more than that along while I was doing the problem. All right, so now that tells me that the moles, if I want to calculate moles of 50 grams of acetic acid, if I have 60.06 grams of acetic acid, that's equal to 1 mole of acetic acid. These cancel, right? And I'm going to get if I put that in my calculator, I'm going to get 0.8325 moles acetic acid, okay? And then, now I'm finally ready to calculate my molarity, all right? So for my molarity, I've got, that's going to be easy, right? So my molarity is 0.8325 moles divided by, we chose 1 liter to make this easy, right? So it's going to be 0.8325. You guys with me? Okay. All right, so now we can do our ice table, all right, because we have a concentration. So we have 0.8325 molar is our starting concentration of acetic acid. we start with 0 of the other two. All right. I'm going to erase my acetic acid here so I can move the rest of this stuff down out of the way. Now, what's our change going to be? I put in all acetic acid. I have all the reactants. I have none of the products. What's our change in acetic acid? Minus X. And if one acetic acid goes away, how many acetates, the base, do I get? 1. So plus X. And how many H pluses? The same thing, right? Okay. And then, so down here, go ahead and set up what the final equilibrium concentrations are. And I'm going to remind you that our Ka is equal to 1.8 times 10 to the negative 5th. Okay. So go ahead and set that up. Yes.
So we're starting all of this. So this all this numbers has to go. So have to do something to go back. So that is what so we assume yeah, I think so.
Okay, let's go ahead and look at this.
Yeah. Yeah.
So for this problem then, what I'm going to have down here is 0.8325 molar minus X. And then over here, my final concentration of the base is going to be X. And my final concentration of the, or the conjugate base, I should say, and my concentration of H plus is going to be X. All right? Now we've already talked about how much we all hate the quadratic formula, right? Maybe you all don't hate it. Maybe some of you love it, and I apologize for disparaging your quadratic formula, buddy. But I don't like it, and so I'm happy to see that I've got a really small equilibrium constant here. So what that means is I'm not going to make much of these, but I'm still going to make some, so I have to keep those, right? But however much of this goes away is going to be really small compared to this, so this can go away. And when this goes away, I don't have to do the quadratic formula. So I am going to ignore that part because it's going to be super small and I'm going to lose it in the significant figures. So now we're ready to solve this. Right? What's our equilibrium concentrations of these things going to be? We want pH, but let's figure out the concentrations first. So that's going to be Ka is equal to, what do I do here? Somebody tell me. What goes on top? X for, right, that's my products are these, right? So one of my products is X and the other product is also X. And on the bottom, I only have one reactant and it is a number, which I'm thrilled to see. There's no X down there. And that's going to be equal to, well here, I'll stretch it out. That's equal to that, right? And so now what I can do is I'm going to go ahead and rewrite it. I'm going to put the Ka over here, 1.8 times 10 to the negative 5th is equal to X. I'll X squared it now to over 8.325 molar. I can multiply both sides times that, 8.325 molar, 0.835, molar. Okay, remember when we're dealing with these equilibrium constants, we're going to have a unit problem here in that I'm going to take the square root and I've only got a molar. These things are dimensionless, so just don't worry about the units here. Okay, we're not going to be able to fix that easily. And so this over here becomes, I think it's 1.8 If I multiply these two together, I'm going to get 1.499 times 10 to the negative fifth. And that is equal to x squared. And then if I could put that in my calculator, so 1.499 E is a good practice for your E key, okay? I had somebody last hour who was having problems with this in this particular case. So, and then I'm going to go ahead and I'm going to take the square. This is also a good reason, I don't know, I think I did it in this help session last week. I was trying to skip steps in algebra and I was making mistakes like forgetting x squared, forgetting to square root things. This is also a good reason to actually show all your steps because then you don't forget things. And so I'm going to take the square root here and I've got x is equal to 0.00387. Is that what other people got? Okay, molar. Okay, and that is equal to, if we go back to our ICE table, that's equal to our concentration of our conjugate base and of our H plus, right? So I'm going to write that. The problem doesn't ask for this, but if I wanted the concentrations at equilibrium, I'm going to write that right down here. So that my professor knows I know what goes where. They don't know, it's just know I know how to solve for x. Does that make sense? So those are those concentrations. And then our concentration of our reactant is what we started with because we neglected the change. It's a really small thing. And it indeed is a really small number. So our concentration of CH3COOH, our acetic acid, is 0.8325 molar. It did not change. Okay, this number here is actually big enough that I would take a little thing off, but it's going to wash out when we do our sig figs anyway. Questions? All right, final bit here. We've got 3 minutes. You guys may get to leave early, just a little. Okay, but we need to calculate the question asked for the pH, right? What is the resulting pH? Right there. Okay, so now we need to figure out the pH. What here do I use to figure out the pH? The H plus concentration, right? Our pH is equal to the negative log of our H plus concentration, which is negative log of 0.00387 molar. Okay. If I was being asked for these things up here, the correct sig figs would be I'd adjust it to 1 sig fig. Okay. I'm going to try to not do that on problems. I don't like one sig fig. There's just way too much error in terms of rounding there. So down here, though, I'm going to go ahead and take the, I'm going to go 0.00. Your calculator may do this differently as we figured out earlier, log, and then I make it positive. And so I get that the pH is equal to 2.4, and that's the pH, okay? I do not round it to 1 sig fig to 2 because, in this case, because the sig fig is the number afterwards. This is like the power you raise it to. Questions? Yeah.
So would it always be just 1 after the decimal, or does it matter about the sig figs?
What you should do is you should match the number of sig figs here is after the decimal, whatever matches your problem. So this is 2.4 because I had 5% as 1 sig fig. If I'd had 5.00%, this would have been 3 sig figs to be correct.
Okay.
But just to be safe, right? Remember, you need to be close. Never just have one number here.
Yeah.
Okay.
Thank you.